In this lesson, we wrap up our look at redox chemistry and survey several important organic oxidations. One of the most classic oxidations is the Jones oxidation. A Jones oxidation uses acidic chromium 6, often referred to as a Jones reagent. Typical conditions include a mixture of either chromium trioxide or sodium dichromate in sulfuric acid. The general pattern of Jones oxidation is that it will oxidize oxygen containing functional groups once for each hydrogen attached to the functionalized carbon. The first example shows a primary alcohol undergoing Jones oxidation to give a carboxylic acid. The functionalized carbon in the reactant has two hydrogens attached, so it will be oxidized twice, from the first redox level to the third redox level. In the next example, we see a secondary alcohol undergoing Jones oxidation to give a ketone. The functionalized carbon in the reactant has only one hydrogen attached, so it will be oxidized once, from the first redox level to the second redox level. Next, we see a tertiary alcohol subjected to Jones oxidation conditions. The functionalized carbon in the reactant has no attached hydrogens, so it will not be oxidized, and the alcohol is simply recovered. Not surprisingly, aldehydes can also be oxidized with acidic chromium 6. In this example, we see an aldehyde undergoing Jones oxidation to give a carboxylic acid. The functionalized aldehyde carbon in the reactant has one hydrogen attached, so it will be oxidized once, from the second redox level to the third redox level. In the last example, we see a ketone subjected to Jones oxidation conditions. The functionalized carbon in the reactant has no attached hydrogens, so it will not be oxidized and the ketone is simply recovered. There are also some selective alternatives to the Jones oxidation that can be synthetically very useful. Some special oxidations can be stopped at the second redox level, even when further oxidation is possible. One method is the oxidation of an alcohol with pyridinium chlorochromate, or PCC. The reaction must be kept dry to avoid overoxidation. In the first example, we see a primary alcohol treated with anhydrous PCC to give an aldehyde. Even though the functionalized carbon of the starting primary alcohol has two attached hydrogens, the reaction stops at the second redox level. In the second example, a secondary alcohol is reacted with anhydrous PCC to give a ketone. Because the functionalized carbon in the reactant has only one hydrogen, oxidation with either PCC or Jones reagent would provide the same ketone product. Another oxidation that can be stopped at the second redox level is the Swern oxidation. In the example, we see a primary alcohol subjected to Swern oxidation to give an aldehyde. The reaction requires a mixture of dimethyl sulfoxide, or DMSO, and oxalyl chloride. These two reagents react to form a sulfonium chloride that acts as the oxidizing agent in the reaction. The alcohol attacks the sulfonium chloride, and a base, such as triethylamine, removes a proton from the carbon, forming a carbon-oxygen pi bond and expelling dimethyl sulfide. Another useful alternative to the Jones oxidation is the Tollens oxidation. This reaction selectively oxidizes aldehydes to form carboxylic acids using basified silver oxide. Other functional groups do not react under these conditions, allowing the selective oxidation of an aldehyde in the presence of an alcohol. In the example, we see acetaldehyde undergo a Tollens oxidation to give acetic acid. Alkenes and alkynes can also be oxidized. Epoxidation is the oxidation of an alkene to form an epoxide, a three-atom cyclic ether. The reaction is often achieved via treatment with a peroxy acid, essentially a carboxylic acid with an extra oxygen. A commonly used peroxy acid is metachloroperoxybenzoic acid, or MCPBA. In the example, we see cis-2-butene epoxidized using a peroxy acid. Note that the reaction is stereospecific. The two methyl groups are cis in the starting alkene and remain cis in the cyclic product. Alkene epoxidation using a peroxy acid has a concerted mechanism. The alkene accepts an oxygen from the peroxide, forming a carboxylic acid as the byproduct. Alkenes can also undergo dihydroxylation, the addition of two hydroxy groups to the pi bond. The reaction forms a vicinal diol and can be achieved using either potassium permanganate or osmium tetroxide. In the first example, we see cis-2-butene treated with cold, basified potassium permanganate to give 2,3-butane diol. In the second example, we see cyclohexene treated with osmium tetroxide and hydrogen peroxide to give 1,2-cyclohexane diol. The reaction is syn-stereoselective, and the two hydroxy groups are added to the same face of the alkene. This is because both oxygens are added to the pi bond at the same time from the metal oxide, necessitating a syn addition. Similar treatment of an alkyne results in the formation of a 1,2-dicarbonyl. In this example, 2-butyne is oxidized to give 2,3-butane dione. Alkenes and alkynes can also be oxidized via ozonolysis. Ozonolysis is the oxidative cleavage of a carbon-carbon pi bond using ozone. Alkenes are typically cleaved into 2 carbonyls, and the specific products vary depending on the workup conditions used. The first example demonstrates a reductive workup with dimethyl sulfide or zinc metal. Under these conditions, vinyl hydrogens are preserved. In this case, the left carbon is oxidized to an aldehyde and the right carbon is oxidized to a ketone. The second example demonstrates an oxidative workup using hydrogen peroxide. Under these conditions, carbons with a vinyl hydrogen are further oxidized to give a carboxylic acid. In this case, the left carbon is oxidized to a carboxylic acid, and the right carbon again oxidized to a ketone. Alkynes can also undergo ozonolysis. Ozonolysis of an alkyne results in the formation of carboxylic acids, and requires only water in the workup. In this example, 2-butyne is cleaved into 2 molecules of acetic acid via ozonolysis. Another oxidative cleavage similar to ozonolysis is the cleavage of vicinal diols using periodate. Because vicinal diols can be prepared from alkenes, the reaction provides a 2-step alternative to ozonolysis for the cleavage of alkenes. In the first example, we see 2,3-butane diol cleaved with periodate to give 2 molecules of acetaldehyde. The reaction is considerably faster when the 2 hydroxy groups are aligned in the same direction. In the second example, we see that the cleavage of cis-1,2-cyclohexane diol is considerably faster than cleavage of the trans isomer. This is because the reaction proceeds through a cyclic periodate ester intermediate, which is more readily formed when the 2 alcohols are in close spatial proximity. We'll wrap up our survey of oxidations with a brief look at the Baeyer-Villiger oxidation. The Baeyer-Villiger oxidation is the oxidative cleavage of a ketone with a peroxy acid to give an ester. Essentially, an oxygen atom is inserted between the carbonyl and one of the adjacent alpha carbons. In the example, we see 2-butanone reacted with a peroxy acid to give ethyl acetate. Regioselectivity is a concern, and the reaction is selective as to which of the 2 alkyl groups attached to the carbonyl migrates to the newly introduced oxygen. The migration propensities are shown here. As you can see, the general trend is that the bond to the more highly substituted alpha carbon will be cleaved. If we look back at the example above, the primary alpha carbon on the left of the carbonyl is more highly substituted than the methyl alpha carbon on the right side of the carbonyl. Thus, the bond to the ethyl group is cleaved preferentially to the bond to the methyl group. The reaction mechanism begins with the nucleophilic attack of peroxide onto the carbonyl of the ketone. In the next step, the tetrahedral intermediate is deprotonated. In the final step, the carbonyl pi bond reforms, forcing one of the attached alkyl groups to migrate onto the adjacent oxygen, expelling a carboxylate in the process.